Okay, so for this video, we're going to focus on now the velocity and acceleration of an oscillating object. And our starting place is going to be right here, okay, with our position function. So remember that velocity would be equal to the derivative of the position with respect to time. And we can take the derivative of this, okay? So dx dt would be equal to we take the derivative of this inside, which would just be omega. We have a omega, and then times the derivative of this cosine part. Derivative of cosine is negative sine, so put a negative up front. So negative a times omega times sine of omega t plus phi. Okay? And we're actually going to start writing, instead of a, we're going to start writing x sub m, representing the maximum displacement. All right, this is just another way of saying amplitude. Okay, which means that this right here would be negative x sub m omega m sine omega t plus phi. Okay, and that would be equal to our velocity equation. Okay, so before we go any further, let's just think about this. Okay, if we have a sine graph and a cosine graph next to each other, we'd say that this position represents one full oscillation. So if we're starting here, that'd be cosine, so this might be position, and then sine would be like this. Alright, we can do better. Sine would be like this. Okay? And so the question is, if this is position and that's velocity, at what position is our velocity maximized? So at what position does the greatest velocity occur? Okay, and hopefully you're seeing that it happens at this position right here and this position right here. And what that tells us is at these equilibrium spots, when it's passing through its equilibrium position, that's when its velocity is at its greatest. Okay, and it makes sense because that's the point where no forces are actually acting on the object. Okay, the next question I have for you is, when are the velocities equal to 0? At what positions are the velocities equal to 0? Well, hopefully you see that occurs at these maximum positions. So here we have a velocity of 0, and here we have a velocity of 0. Okay, it's occurring at those places where it's turning around. Okay, so you have an oscillating spring. We have zeros when that spring is turning around. Okay, and so if we look a little closely here, this piece right here represents the amplitude, and so the maximum velocity is equal to, and since it's a maximum, it's a magnitude, so we can ignore the negative. So the max velocity is equal to x sub m times omega. And so we can even write it like this: v equals x sub m, equals v sub m times sine omega t plus phi. Okay? And now we have our velocity function. So this represents the velocity, and it's a negative, put that negative in front. So now we have a function representing the velocity of this oscillating object. Well, we can take another step because the derivative of velocity represents acceleration. So if we continue taking the derivative, we'll do it from this one right here. So we get negative x sub m. We're going to multiply by omega again. So omega squared, derivative of sine is cosine omega t plus phi. Okay? So we get really the same thing that we started with times omega squared and times negative. Okay, so let's draw our acceleration function. Alright, our acceleration would look like, it would start down at the bottom. I ran out of room here. So it's going to come like this. And then it's going to come back down like that. And come down like this. Okay? And so you'll notice that it's the inverse, or it's the negative of this position graph. Okay? We'll see that the acceleration is 0 when this object is at its equilibrium position, and the acceleration peaks when it's at its positions furthest away from the equilibrium position. Okay, and I also want to show you this. We can rewrite this as A equals negative omega squared xm cos omega t plus phi. And so A is equal to then negative omega squared. I can replace all of this with this because it's this piece right here times x of t. So A of t equals negative omega squared times x of t. Alright, and this is actually a really huge deal. We'll talk about it more in the next video. But this basically is like the condition for simple harmonic motion to happen. Okay, so here we have a scenario. There's this oscillating spring. It completes 10 oscillations, spring and mass system, completes 10 oscillations in 5 seconds. The amplitude of the oscillations are 40 centimeters or 0.4 meters. I want you to start off writing a position function, or a function for the position of this mass. Okay, so position with respect to time, we put our amplitude x sub m 0.4 meters times cosine, and we're going to say phi is equal to 0. Got to find out what omega is. That's going to be 2 pi over the period, which in this case is 10 oscillations in 5 seconds, or 5/10, or 0.5 seconds. Okay, so that means our omega is going to be equal to 4 pi. Okay, next I want you to write a function for velocity and tell me what the maximum velocity is equal to. Okay, so we're going to take the derivative of this, so multiply 4 pi times 0.4, giving us 1.6 pi, and this becomes now meters per second, times, it's going to be negative, times sine of 4 pi t. The maximum velocity is going to be negative 1.6 pi meters per second. Alright, next I want you to find the acceleration function and tell me what the maximum acceleration is equal to. Okay, and this would be positive because it's a magnitude. Alright, so we take the derivative of this. 4 pi times negative 1.6 is going to be negative 1.6 pi. Going to be negative 4.8 pi squared meters per second squared times cosine of 4 pi t, and the magnitude of our maximum acceleration at those peak points is going to be 4.8 pi squared meters per second squared. Okay? And there we go. We could also find the maximum acceleration using this. Okay, and so if we say 0.4 meters times 4 pi radians per second, that's going to give us and that's squared 4.8 pi squared radian or meters per second squared too. Okay.